Okay, so in this lecture, we discuss the concept of an invariant subspace. The concept of an invariant subspace. Okay. So we have already discussed about eigenvalues, eigenvectors, and what is diagonalization, and certain characterizations of diagonalization. The goal behind studying invariant subspace is again to conclude a certain characterization of a diagonalizable operator. Okay. So in this case, we deal with the characterization of the diagonalizable operator in terms of the minimal polynomial. Right? So if you remember what minimal polynomial was, so it was the least degree monic generator of the ideal of annihilating polynomials of a certain linear operator, right? So we start with the concept of an invariant subspace. Okay. So let us straight away come to the definition. Let T be a linear operator. Let T be a linear operator on a vector space V over the field F. So a subspace W of V is said to be T invariant or invariant under T if for all elements alpha in W, T of alpha is again in W. That is, the image of W under T is a subset of W. Okay. So in this case, we say that W is a T invariant subspace or a subspace invariant under the linear operator T. So let us come up with certain trivial examples of an invariant subspace. Now, if T is a linear operator, then the range of T and the null space of T are T invariant. And the proof is fairly simple. Observe that. Suppose you take an element from N. So alpha is an arbitrary element of N. We need to show that T of alpha is inside N. Hence, because alpha is an arbitrary element from the null space and T of alpha is inside N, so it makes it trivial to see that the image of the whole null space under the linear operator T is inside the null space, right? Now, since alpha is in Nt, then T of alpha is equals to 0. But W is a subspace, right? Or rather, I can say in this case, the null space is a subspace. So the null space is a subspace, that means 0 must be inside the null space. So this is inside the null space, right? And so that's proved. Because for any element you take from the null space, its image will be equal to 0, and 0 is an element of the null space itself. So T of alpha is inside the null space for all alpha being an element of the null space, right? Number 2, that is the range space is T invariant. Okay, so let alpha be an element from the range space. Okay, so we need to show that T of alpha is inside the range space, right, or the range of T. Now, since alpha is an element of the range space, so that implies there exists an element, say small v in capital V, such that T of small v is equals to alpha, right? Right. But that implies that what is T of alpha? Then T of alpha is equals to T of V, right? Now this is obviously inside the range space as well, as since T is a linear operator, so its codomain is the vector space V, right? Therefore, T of V is inside V for all vectors small v and capital, right? So that implies the image of TV for every vector small v is inside the range space. But that typically implies the image of alpha under T is inside the range space, right? So it's proved again, right? Because alpha was chosen arbitrarily from the range space. Okay. So these are some trivial examples. Then the other trivial example is simply if W is the zero subspace. Okay. So let T be a linear operator on V and let W be the zero subspace. Okay. Then obviously if you choose alpha from W, then that implies alpha must be equal to 0, but that implies T of alpha must be equal to 0 and 0 is inside W. So that implies T of W is contained in W. In fact, it's equal to W, right? Furthermore, if W equals to V, then it's obvious because of the fact that T is a linear operator. So any element you choose from W, that's an element of V, and the image of an element of V will be inside an element of V because T is a linear operator, right? If W equals to V, or rather we can frame it like this, that for all T in LVV, V is T invariant. V is T invariant, right? Let us take the next example. So, okay, so this is slightly a non-trivial example. Okay, so let T and U be linear operators on a vector space V over F. T and U commute. T and U commute. That is TU is equals to UT, and this happens for every element. So we are not mentioning the element exactly. So T of U is equals to U of T. So that's the commutativity of the linear operators T and U. Okay. Then, so if T and U commute, then the range space of U and the null space of U are T invariant. Obviously, you can also kind of claim that the range space of T and the null space of T are U invariant. So it's a symmetrical statement. So the proof of this is uh, kind of trivial. So if you choose an element from the null space of U, let's say let V be an element of null space of U, right? So to show T of V is inside the null space of U, right? Now since V is in the null space of U, right? So that implies UV must be equal to 0. Right? But if UV is 0, then TU of V is again 0. Right? But so it works as a composition operator, right? So T of UV is equals to 0. But that implies, so since T and U commute, so that implies UT of V is 0 as well. Right? But if UT of V is 0, then that means T of V is inside the range space of U. Right? See, if T of UV is equal to 0, then that implies, since T and U commute, so that implies UT of V is equals to 0. And T of V is an element from the vector space V. Right? It's a vector. So T of V must be inside the, it must be inside the null space of U. Right? So therefore the null space of U is T invariant. And on an analogous set of statements, we can also show the range space case. So let alpha be an element from the range space of U. Then obviously there exists a vector small v such that U of v is equals to alpha, right? We need to show T alpha is inside range space of U. So we need to frame the element T alpha from here, which is quite obvious that T U of v is nothing but T alpha. But T and U commute, right? So it's U T of v is equals to T alpha. Now T of v is an element of v. So that means U of TV, which is basically equals to UTV. So it's inside the range space of U, but that implies T of V is inside the range space of, sorry, T of alpha, right? T of alpha is inside the range space of U, right? So it's quite obvious from, right? Okay. One more example you can think of is if you choose a collection of all polynomials over the field f of degree less than equal to n, then you can think of the linear operator, which is the differential operator. Okay. Then you will obviously notice that W is a so it's D invariant. Okay. Let me just frame this as an exercise. Let V be the space of all polynomials. Be the space of all polynomials. One second. Yeah. So let V be the space of all polynomials over the field F. Over the field F, and let W be the collection of all polynomials over F of degree less than or equal to n. Okay. Show that W is D invariant where D of any polynomial fx is f dash x. Okay. So this is the differential operator, right? If you recall, it is the differential operator. Yep. And I think it's very easy to observe because if you differentiate a certain n degree polynomial, then the new polynomial you will be getting, it will be of degree n minus 1, right? So it will obviously be inside W as well. So any polynomial you take from W, you differentiate it, you will get a polynomial of degree less than the previous one. So it will obviously be inside W. Okay. So we were in example number 4, I guess, right? Which example? What was the index of the example? Example number 3, right? So example number 4. Okay. And this is an important one. So let T be a linear operator on a finite dimensional vector space. Over a finite dimensional vector space. Let C be an eigenvalue of T, and alpha, or let's say W, be its associated eigenspace. That is, it is the collection of all eigenvectors associated with this eigenvalue C. So let me name this vector space as V over F. Okay. Okay. Now observe if you choose any alpha from W, then you have T of alpha is equals to C times alpha, right? This is from the direct definition of what eigenvectors are. We claim that the image of alpha under T is inside W. That is typically speaking that eigenspaces are T invariant. Eigenspaces related to the linear operator are invariant under that linear operator. Okay, so we claim this. So how can we do it? Observe that. So proof, let's say, now we have T of alpha equals to C of alpha, right? What is T of alpha? So it's T of C alpha, but T is a linear operator, so C comes outside. So it's T of C alpha, sorry, C times T alpha, but T of alpha is again C alpha, so it's C squared alpha, right? Or we can directly think of it as, we don't actually need this because we can think of it as, yeah, this will do, because observe that, we don't actually need this because this statement directly implies that T of alpha is an eigenvector, corresponding to the eigenvalues, right? Corresponding to the eigenvalues. Got it? So this implies T of alpha must be inside W, right? So basically eigenspaces are T invariant under the linear operator associated with it, right? Clear? And that's quite an important one. Got it? Okay. Okay. Now, now this is a certain observation. Now see, whatever we are studying under these specific lectures are basically the matrix representations of linear operators in a simplified form, right? So one obvious goal of this lecture should be to attain some simplified structure of a linear operator. Since we are talking about invariant subspaces, so we need to check what the matrix of an invariant subspace looks like, right? So it's an obvious target, you might say. So let V be a finite dimensional vector space over the field F. Okay. Let W be T invariant. Let W be T invariant. So W is T invariant. T invariant subspace of V. So W is a T invariant subspace of V. Okay. Now, since W is a subspace of V, so we obviously have some basis of W, right? Right. So let B, which is given by the vectors alpha 1, alpha 2 till some alpha n, is the basis of V. Is a basis for V such that B dash, which consists of the same vectors up to some certain vector. So let's alpha 1, alpha 2 till some alpha r be a basis for W. So actually what are we doing is that we are using the concept of extending a vector, right? So we have a certain vector for a subspace. We know that we can extend that vector to get we have a certain basis for a subspace, so we can extend that basis to get attain a basis of the whole space. So if B dash is a basis for W, W is a subspace of V, so we can extend this to get this basis, right? So we are kind of reversing the statements. So is an ordered basis. So we should be concerned about ordered basis. Is an ordered basis. So this is also an ordered basis for W. Okay. So obviously from here it's clear that dimension of W is equals to R by the way these bases is given. Now let A be the matrix of T with respect to B. Okay. Then for each element inside the basis B, what is T of alpha j can be written as? So it is some scalar multiple of all of these elements. So it's of the form say Aij, alpha I, I equals to 1 to n. But this is pretty trivial from how we constructed the matrix of a linear transformation, right? Right? Is it clear? Now W is T invariant. Since W is T invariant, then T of alpha j is inside W for all j less than equal to r, because each vector alpha j for j less than equal to r is a basis element of W. So they are individually inside W, right? So therefore, or we can say it like this, that T alpha j, which is equals to summation over, say I equals to 1 to r aij alpha I. So this is inside W, to be very specific. Okay. But what does these two statements immediately imply? So therefore, aij must be equal to 0 if j is less than equal to r and I is greater than r, right? Right. I guess it's pretty obvious to notice this from here, right? So if so, therefore A, or we can say A has this block form, right? So we have the matrix B, C, D, and the elements under B are all zeros, where B is an R cross R matrix, right? B is an R cross R matrix. This statement is an immediate conclusion of this representation, nothing else. Okay. Because whenever I is greater than R, so they all must be 0, because we are concerned about the elements j less than equal to r, right? Because what are the basis elements of W? So it's alpha 1, alpha 2 till alpha r, right? So if I is greater than equal to r, aij must be 0, because we are concerned about the elements of W, right? And the elements of W are spanned by only the first r vectors, right? So whenever I is greater than r, then the scalars must be equal to 0. We can think of this as something of this sort. So it's of the form, say a1j alpha 1 plus a2j alpha 2, and so on till we get arj alpha j, but the rest of the elements are all 0, right? So 0 times alpha r plus 1, and so on till 0 times alpha n, right? So these constitute of elements of W. So from this representation we get B to be an R cross R matrix, and trivially observe that B is basically the matrix of the linear operator T when restricted to W, right? So we will come to that. So B is an R cross R matrix with respect to the coefficients of this form, and then we can simply relate. So C and D constitute of the matrix of T with respect to elements outside W. So when B is an R cross R matrix, right, then you have C is so it must be an R cross n minus R matrix, and D is a n minus R cross n minus R matrix, and D is a n minus R cross n minus R matrix, right? So if T of W is defined as T restricted to W, then this is what I was just saying. So it's the B is basically the matrix of TW with respect to the basis on W. So this matrix B. Okay, I've used same notations, right? So let this be BV, let this be BV, and let this be BW. So I've used terms W, right? So yeah, I guess it will do. Right? Clear? Okay. Okay. What do we mean by restricted operator? So this means TW of alpha must be equal to T of alpha for all alpha in W. Okay, is it clear? Now, having this representation of A, what can we say about the characteristic polynomial of A? Now, what is the characteristic polynomial of A? So, the characteristic polynomial of A is determinant of xi minus A, right? But xi minus A is of this form, right? So, it's minus 1 to the power n, determinant of b minus xi r c 0 d minus xi n minus r. Where I is the where I some k represents the identity matrix of dimension equal to k. Okay, so it's obvious, right? So from here the determinant calculation simply gives you it of the form sum xik minus b times xi n minus k minus d. Now this is the characteristic polynomial. So we can, this is the characteristic polynomial of the matrix of T with respect to the basis PV, and this is the characteristic polynomial of the restricted operator of the invariant subspace W in the T invariant subspace W with respect to the basis of W, right? So what does this statement say? Therefore, the characteristic polynomial of the restricted operator of the T invariant subspace W divides the characteristic polynomial of the whole operator T with respect to the basis of the whole vector space, right? Is it clear? Now on a similar set of statements we can also show that the minimal polynomial of the restricted operator will divide the minimal polynomial of the operator T. So one sec. Yeah. Okay, so observe that so if A is of this form, right, it's of this block diagonal form, these forms are called block diagonal forms or block forms, I should say, because this is exactly not a diagonal matrix, so I should not use the term block diagonal form, but it's indeed a block form, block matrix representation, you might say, block matrix representation. Okay, so observe that from here, what is a to the power k for any integral power k? So it's of the form b to the power k c to the power k 0 d to the power k, right? So this implies therefore if any polynomial annihilates A, it annihilates D as well, right? B as well. In fact, D as well. So it annihilates B as well. Therefore, if P is the minimal polynomial of A and Q is the minimal polynomial of B, then observe that P of A equals to 0, but that implies P of B must be equal to 0. Now, since Q is the minimal polynomial, so it's the least degree monic generator of all polynomials which annihilate B. So that means Q must divide P. So the minimal polynomial of B must divide the minimal polynomial of A. Right? Is it clear? So, okay, let us come to an example of invariant subspaces. Let T be a linear operator on the vector space R2 let TB be the matrix of T, with respect to the standard ordered basis. Standard ordered basis of R2. Let A equals to TB be the standard with the matrix of T with the standard order basis R2, where we give the matrix of A as 0, -1, 1, 0. Right? Then claim R2 has only two invariant, I should say two T invariant subspaces. Two T invariant subspaces, which are the zero subspace and the whole subspace R2. Now, zero subspace and whole subspace R2 are indeed T invariant, right? That is quite trivial to observe. Now, so if there exists another T invariant subspace, then the dimension of that subspace must be equal to 1, because any subspace of R2, if it's non-trivial, that is, if it's non-zero and it's not equal to R2, then it can have dimension 1, right? So we need to check if there exists a one-dimensional T invariant subspace of R2 or not. Right? So let W be a proper subspace of R2. So this trivially implies that the dimension of W is 1. Right? Let W be T invariant. Okay. So that implies if any element you choose from W, say alpha, then T of alpha must be inside W. Right? Right. Is it clear? Now, since W is one dimensional, therefore there exists and it's obviously non-zero. So let it be the non-zero. So there exists a non-zero vector B such that W is spanned by this non-zero vector B. Okay, B is obviously inside W. Now, if W is spanned by this non-zero vector B beta, then alpha must be some scalar multiple of beta. Therefore, there exists some C in F such that F, or rather, in fact, since we are talking about R2, so we can consider the scalar from R such that alpha is some C times beta. Right? But that implies beta can be written as 1 over C times alpha. Now, T of alpha is inside W. Right? T of alpha is inside W. Since T of alpha is inside W, so that implies T of alpha is some other scalar multiple of beta, right? Because W is spanned by beta, and T of alpha is an element of W, so it means it's another scalar multiple of beta. But beta is 1 upon C times alpha, right? So it's some D upon C times alpha. Right? And alpha is obviously non-zero. We have chosen a non-zero element from alpha. Okay, so where let's say alpha is non-zero. Clear? Got it? Okay. And alpha is non-zero, which it is trivial from the fact because beta is a non-zero vector, and C, since we are defining the element 1 over C, so C must be equal to non-zero. The scalar must be equal to non-zero. So if C is non-zero and beta is also a non-zero vector, so alpha is trivially non-zero, right? Right. So if I consider D by C to be a scalar T, then that implies T of alpha is some T times alpha, right? Where T is an element from the field X. Okay. But this means that therefore T is an eigenvalue, right? From the definition. So T is an eigenvalue of the operator T. Right? and T is an element from R. But observe that we have, I think we have dealt with this very example previously also. But observe that T admits no eigenvalues. T admits no eigenvalues over R, because as the characteristic polynomial of T is x square plus 1, which is irreducible over R, right? Therefore, a contradiction, right? Therefore, a contradiction, because we got an eigenvalue from R, but there shouldn't be one. Therefore, a contradiction. Thus, there does not exist one-dimensional T invariant subspace of W, sorry, of R2 for the provided linear operator. Is it clear? Okay. Yeah. Okay. Is it clear? Okay. So let us come to the next important concept of this lecture, which is, let us get into a definition as well. So let T be a linear operator on a finite dimensional vector space Vn. Okay. Let W be a subspace of V. Let W be a subspace of V, and let alpha in V be any vector, be any element. Okay. Define St of alpha W to be the set of all polynomials, P, obviously over F, such that the image of alpha under the operator P of T is inside W. Okay. Clear? Is it obvious? Now, this set St of alpha W is non-empty, as the minimal polynomial and characteristic polynomial of T are in this set. And why is it so? Because observe that Pt of alpha is equals to 0 and Ct of alpha equal to 0, where P and C are the minimum and characteristic polynomials respectively, right? And 0 is an element of W, because W is a subspace. So Pt of alpha is inside W and Ct of alpha is also inside W. Therefore, P and C are elements of St alpha W, right? So it's clearly non-empty. And this is, we can talk about the minimal and the characteristic polynomials, because we have considered that V is a finite dimensional vector space, right? Further, observe that St of alpha W is an ideal of Fx. Now I keep this as an exercise. It's pretty easy to derive this fact. So you just need to check if F and G are elements from St alpha W, then F minus G is in there, and any element P you choose from the from the field fx, then p, f and fp are in st alpha w as well. Okay. Okay. So it forms an ideal. Is it clear? Is it clear? Now, if since this is an ideal of fx and fx is a PID, right? It's a principal ideal domain. It's a principal ideal domain, right? So that means that this ideal has a least degree monic generator, right? Therefore, st alpha w has the least degree monic generator, say qx, which is called the T generator, sorry, T conductor of alpha into W when W is invariant, when W is invariant under T, Basically, this whole set is called the T conductor of alpha into W. Is okay. So what I try to say is that st alpha W, this whole space is called the it is actually called the T conductor of alpha into W. The term conductor actually it is a more standard term which it is preferred by it's preferred because it kind of has a literal sense which gently leads a vector alpha into W. Right? So if W is invariant under T, then the monic generator itself is precisely it abides by the term of a conductor. So let me just speak of it in this form. Observe that if W is invariant under T, then it's invariant under any integral power of T, right? It's invariant under any integral power of T such that R is a natural number, so it's any integral power of T. So that implies W is invariant under the operator f of T, where f is an element of capital Fx, right? In this case, this definition abides. Okay. So if W is T invariant, then obviously this will admit a least degree monic generator. So if W is T invariant, then this least degree monic generator is called the T conductor of alpha into W. Okay. Is it clear? Now if W is 0, is the zero subspace. If W is the zero subspace, then for all vectors alpha in V, st of W alpha or alpha W whatever, so it will be the set of all annihilating polynomials, right? Of all annihilating polynomials of alpha under T, right? That is if f of x is in st of W alpha, then f of T of alpha must be 0, right? Therefore, the T conductor of alpha into W equals the T annihilator of alpha under T, right? So it's the P annihilator of. Okay. Moreover, observe that if W is equals to V, what happens? If W is equals to V, then ST of W alpha is nothing but ST of V alpha. So it has a monic generator. It has a monic generator P such that P divides G. Sorry, P divides Q. I have used the notation Q. So P divides Q. Right? So what does this actually mean? So this actually means that the minimal polynomial will divide the the conductor will divide the minimal polynomial, right? Let me just explain this a bit in the next page. This requires quite a bit of an explanation. Just explain it. So, one second. Yeah. So, what I'm trying to say is that see, we have already spoken of the fact that ST of alpha in W has the minimal polynomial, right? It has the minimal polynomial, right? Right? Say P. Now, since Q, which is the T conductor, of alpha into W, it generates or is the least degree monic generator of this set. Therefore, Q must divide any polynomial inside it. So Q must divide P, right? So therefore the T conductor divides the minimal polynomial of T, right? That's what I actually wanted to say. Is it clear? So let this lecture be up till this much, guys. In the next lecture, we will be starting with the concept of what a triangulable operator is. Okay. So meet you guys in the next lecture.